Thanks. So let me recall from yesterday where we were. So we had X, say smooth and proper projective, whatever variety over K. K, say a perfect field of positive characteristic. And I explained to you, or I mentioned, or I introduced that there are these cohomology groups called crystalline cohomology, W, crystalline cohomology. These are finitely generated modules over the Witt ring. So this is a discrete valuation ring, complete with residue field little k, and in some sense universal. And somehow the way to think about it is that if the variety X admits a flat lifting over the Witt ring, then crystalline cohomology is simply the deRham cohomology, the algebraic deRham cohomology of the lift. And somehow the main technical issue is to show that if lifts exist, that this is well defined, and in case lifts don't exist, to define it nevertheless. And somehow to complement where I was yesterday, let me also mention that there is Illusie constructed an analog of, I mean, I told you that if you reduce modulo P, there is a universal coefficient formula that relates crystalline cohomology to deRham cohomology. And in deRham cohomology, we have this spectral sequence from the HI omega J to deRham cohomology. And so there is an analog of this in this situation here. It's called the deRham-Witt complex. So this is somehow denoted omega X complex. I will not somehow, you can define this for Wn, for all n. In case n is 1, it's just the deRham complex. And somehow, so for n equals 1, this is the deRham complex. And we have that W omega 0 is really WOX, which we've seen already in the talks yesterday or in the afternoon. So here the cohomology is, so this is Witt vector cohomology. This yields to, this leads to these omega I, HI omega J. And so the thing is that there is a spectral sequence called the slope spectral sequence, slope spectral sequence, which goes from H, P, W. So if I leave out the index, that's just the limit over the WNs, omega Q to crystalline cohomology. It's called the slope spectral sequence, and it always degenerates up to torsion. Oh, I guess it's E1. Yes. Oh, okay. If it's PQ, then it's QP, right? Yeah. So it's like the deRham spectral, Hodge to deRham spectral sequence. And in fact, if you write n here, wn here, and wn here, then for n equals to 1, this really is the Hodge deRham spectral sequence. Degenerates modulo torsion. I should say that even in very nice situations, for example, if X is a hypersurface of degree 4 in P3, then it can happen that this spectral sequence does not degenerate at E1, without, I mean, if you include torsion. So the point is that that these cohomology groups, they may not be finitely generated as W modules. So for example, if you have, as an example, if you take a quartic in P3, this defines you a smooth quartic in P3, that defines your K-free surface. If this K-free surface happens to be supersingular, for those who know what this is, then these cohomology, then I think, I keep on forgetting which one it is, one of them is not finitely generated, and then this spectral sequence has no chance of degenerating without including torsion. I mean, because, I mean, this is finitely generated. So even in very nice situations, the HQ may not be finitely generated. That is, in fact, the torsion. Maybe to say it a little bit. The torsion of that may not be finitely generated. So we have this. So there is an analog of the Hodge deRham spectral sequence in this situation as well. Then, yeah?
Just about torsion. Before you mentioned the fact that when you have the leaf of your variety,
yes.
Zero, then the crystalline cohomology coincides with the deRham.
But I'm not saying that if you lift the variety to characteristic 0, that the Hi omega j coincide with what you get from the Rham-Witt complex.
No. I said before.
Uh-huh.
Because I think that crystalline cohomology is with values over they are modules over the bit range.
Yes.
For you, the deRham cohomology is vector spaces or?
Well, if the deRham cohomology would be vector spaces over little k, like, yeah. Okay.
In this sense, when in terms of my k.
Yeah. Oh, sorry. Okay, so there is the spectral sequence. And let me say, which examples do we have at the moment? In particular, we see already, we have, so this allows one, so what we have at the moment, this is already enough to compute projective n space, complete intersections in it. So can compute. So I should say, this is a rather complicated construction. I will not say anything about this in the sequel. Coming back to crystalline cohomology, so we can compute it in terms of, we can lift projective n space, we can lift complete intersections, and let me also say that, simply to give you an impression, that if you have X to A, the Albanese map, then H1 Chris X it's kind of the things you would expect to have. So you can also lift curves. So we have curves, complete intersections, p to the n. We can always compute H1 if we know what it is for an abelian variety. So if A is an abelian variety, then it's just kind of the usual things you would expect. Then this is the nth exterior power, even with extra structure of H1. So I only have to know what H1 is. And this is just for people who know this. H1 can be computed from the Dieudonné module. So you take the limit over the p to the n torsion. And then there is a way to associate to that you can compute H1 from that, for those who have seen that. What I want to say is that with these sort of techniques, we can already compute, we already know the crystalline cohomology now of projective n space, complete intersections, curves, abelian varieties. We know that we have the usual formulae for under finite morphisms. So you see that, in fact, for most of the varieties that you meet in everyday life, you don't actually have to know what the definition of crystalline cohomology is. You can compute it from that already. Let me now come to the next section, which slightly formalizes this. So if in complex geometry, you learn about deRham cohomology over the complex numbers, and you know at some point what a Hodge structure is. So you have a complex vector space, you have a filtration in it, you have a conjugate filtration in it, you have a rational structure or an integral structure. So, and this is then captured in the notion of a Hodge structure, and then you construct period domains and stuff like that. You do the same here, well, or something similar here. You have a closer look at what kind of extra structure you get from a crystalline cohomology group, and that leads me to, I think that's now section 2, the notion of an F crystal. So the setup is as follows. You have K, a perfect field of characteristic P. You have the Witt ring. Now, on a perfect field, you have this map Frobenius, x goes to x to the p. And so by functoriality, I told you that the Witt ring is functorial in K. You get an induced map, also called Frobenius, on the Witt ring. And now the problem is there are too many F's around in algebraic geometry for Frobenius, so it's customary to call that Frobenius sigma. I would change the, I will use that notation now. So this is name for induced Frobenius. You will see in a minute why, because otherwise you get like formulas later on where there are two F's in it, which means something different. On the other hand, if you have a variety, so what do you get from crystalline cohomology? You get a WK module, so a module over a discrete valuation ring, finitely generated. And of course, for your variety in characteristic P, there is also an absolute Frobenius on that, F from X to X. And by functoriality, you get a Frobenius action on crystalline cohomology. And this is captured then in the following definition. An F crystal, sometimes the F is left out, is a free WK module. M. So we forget about torsion in this setting, plus a map phi from M to M, such that phi is injective and it is what people call sigma linear. You see, Frobenius, in the geometric applications, Frobenius will not induce a linear map, but what it will induce a map that has the following properties. It's additive, so that's the definition, or it satisfies phi of Rm is equal to sigma of R phi of M for all R in W for all M in M. Then let me continue the definition, an F isocrystal is the same, is a finite dimensional, or finite, is a finite dimensional K-vector space. K is the field of fractions of the Witt ring plus, so V, an injective and sigma linear map phi from V to V. And then you can have a notion of morphisms of F isocrystals. This is precisely what you think it is. It's morphisms from M to M, or from from M1 to M2, or from V1 to V2, which are compatible with the sigma linear actions. And then there is another interesting notion, is an isogeny of, let's say, F of crystals, or F crystals, is a morphism of F crystals such that if you tensor with K, that this is an isomorphism. And so, of course, note, let me make an obvious remark. If M phi is an F crystal, then it follows that MK. If you tensor with K, this is an F isocrystal. Okay. And so the main example, of course, is, of course, if you have a smooth and projective variety, X, smooth and projective variety over K, then you set M and you mod out the torsion. This is a finitely generated W module, and then the absolute Frobenius. Induces a map phi from M to M, which is sigma linear. I haven't shown why it is injective, but that's true. Okay. And oh, maybe I should say something. To prove injectivity, you can, for example, use Poincaré duality. I mean, this is, so phi is injective. But I haven't explained to you why. So this M phi is an F crystal. Okay. So this is a way to produce crystals out of geometry. Let me give a purely algebraic way of producing F crystals. Example, this would be from purely algebraically. goes like follows. Let W sub sigma t be the non-commutative polynomial ring so you take polynomials wk adjoint t, however you make it non-commutative in the following sense, such that in the sense that t times w is the same as sigma of w times t for all w in the Witt ring. So it's not commutative, but it's not too bad. And then I do the following. I take a rational number such that R is a natural number including 0, S is a natural number not including 0, and I want that the GCD R and S is equal to 1, so they're coprime. And then I set M sub alpha to be T to the S minus P to the R. And you set phi, the map that sends M multiplies it with T. And then I claim then M alpha comma phi is an F crystal. So this associates to every rational, to every positive rational number, an F crystal. S turns out to be, so this is the rank. So we see that in every rank there exists an F crystal, and this quotient alpha, by definition, is called the slope of M alpha. By the way, for those who have seen, these sort of arguments, so the interesting thing is, if you look here at the slope spectral sequence, why is it called slope spectral sequence and why does it degenerate? The reason is also these here are, if you mod out torsion, are crystals. And this, if you mod out torsion, is a crystal. And then if you look at the spectral sequence, then you see that the higher differentials do not respect the slope, which will tell you by analysis that there cannot be non-zero differentials. And so this is the reason for calling it slope spectral sequence, and it also explains to you why it degenerates at E1 level. It's an observation that you can see that between between crystals of different slopes, there are not that many maps. And so this is kind of the reason why this is called slope spectral sequence, and it also gives you a hint why you should believe in its degeneracy and why it's degenerating at E1. Okay. So what's the point in these? So we have these examples here, and there's an interesting theorem. Which is the Dieudonné-Manin classification. Classification of crystals up to isogeny. So, and it says that let K be now an algebraically closed field of positive characteristic, then the category of F crystals up to isogeny is semi-simple. And the simple objects well, here I'm only discussing those with with non-negative slopes. I mean, there is also, I mean, I should say, I mean, you can also consider crystals of negative slopes, but those will not come from geometry. Well, it's a little bit like looking at Hodge structures with negative weight. So in a sense, what I want to say is that, so what does it tell you? It tells you that from the crystalline cohomology, you get this abstract structure of an F crystal, which is just this module with the sigma linear operator on it. And there is a very easy way, or, well, yes, a very easy way to construct crystals associated to rational numbers. The Dieudonné-Manin classification tells you that up to isogeny, we already understand what crystals are. I mean, it's getting, of course, much more complicated, and we will see in a second why, if you do it without up to isogeny. But at least you see that, well, it should give you an impression that these objects are actually something you can actually work with. And yeah, I think.
So, when we look at the variety, which slopes are occurring in the corresponding crystals?
Can I postpone this question? This is somehow, we will see, there's a theorem of August Mather and others that it will tell you, it will answer you this question, I hope. So, I mean, one thing is already, as I said, that if it's coming from geometry, and this is the reason I'm restricting myself only to positive slopes. If people are doing representation theory, you also see sometimes negative slopes.
So are crystals up to isogeny? Is that a full subcategory of isocrystals?
I think so.
Is it actually equal to isocrystals?
I also think so. Pardon?
You cannot have isocrystals of negative slopes.
I think you can. I mean, I didn't define that. I mean, it's not something meaningful that coming from geometry. It's like looking at negative weight Hodge structures, so to speak. I mean, but I've seen it in representation theory. So definition. So if I have let M be an F crystal over an algebraically closed field now, and then let. So this is the notion for saying. So for isogeny or being isogenous, then it's a direct sum of some M alpha N alpha be as well. So the decomposition, say, under Dieudonné and Manin. And then, then the set of those slopes that actually occur are called the slopes of M. And so we are getting closer to Holger's question. And n alpha times the rank of M alpha is called the multiplicity of the slope alpha. Now, the next thing that you do, so I'm starting now from an F crystal, for example, coming from crystalline cohomology. I look at the decomposition into these, up to isogeny. And then I get these slopes. And then out of that, I construct two polygons. So let M be an F crystal. With alpha 1 so the slopes of M. So I order them well, increasingly. Lambda 1, lambda 2, up to lambda t, the corresponding multiplicities. And then I have associated to M phi. Oh, sorry. I have two polygons. No. One is called the Newton polygon. And I have to explain what this is. So NWT of, or NWNT. So I write it down as a piecewise linear function. So it goes from this to the reals. Well, in fact, it's to the rationals. So 0 goes to 0. This is easy. So it starts on the top left bottom. And it's off slope alpha 1 if 0 lies in this region of slope alpha 2 if lambda 1 etc. So you see in particular it's a convex polygon. And then there is another one, and you see, of course, this polygon depends only on the slopes of M. So in particular, if you have isogynous F, sorry? Oh, yes. Thanks. Yeah, so the idea is that you have slope alpha 1 for as long as you have lambda 1, and then for a lambda 2 section, you want to have slope alpha 2, and so forth. And as I said, it only depends on the slopes of M and of the multiplicities. So in particular, it's an invariant of the crystal up to isogeny. So if you have two F crystals which are isogenous, you will have the same Newton polygon. This is different from the other polygon. Yes? Yeah, and I think, by the way, how I defined this, I mean, yeah, well, so, yeah, you have to check something here. Yeah, that's a perfectly valid question, but I hope it adds up. Yeah, well, it should. And there is another polygon now, another convex polygon associated to an F crystal, which is really an invariant of, which is not an isogeny invariant. So this is called the Hodge polygon. So this depends only on M up to isogeny. So this is not an isogeny invariant. So what you do now is you take M modulo phi of M. Now, WK, the ring of Witt vectors, is a DVR. So every module over the Witt vectors has a free part, and you have this elementary divisor theorem. So you can write this uniquely as a direct sum, I bigger than 1, Wi modulo p to the iw to some. So this is some sort of elementary divisors theorem, because W is a DVR, and you said H naught by definition is rank of M minus I. This. And then you define a second polygon, Hodge, which goes again from here to the reals, which sends 0 to 0, and it is of slope 0, so you have a kind of flat piece if you are between 0 and h naught. It's of slope 1 if you're between h naught and h naught plus h1, and so forth. So associated now, we have these two polygons, and of course the question, so the natural question is, are they related? And the second question is, why is it called Hodge polygon? So in this generality, we have the following proposition, namely, let M. So this is also a convex polygon, I should say. So it also gives you a convex polygon. Then let F be an F crystal. Then the Newton polygon is always on or above the Hodge polygon. Newton polygon lies on or above. Hodge polygon. Now, if I'm now, so I mean, everything is modeled on geometry. So of course, well, it's natural to look at the following. So if I have a, say, smooth and proper variety, so X smooth and project or proper projective over an algebraically closed field of characteristic P, there is a geometric polygon which simply encodes the Hodge numbers. So what you say is that define HI twiddle to be, so fix a non-negative integer, and I define HI twiddle to be the dimension, the k dimension of this so these are the classical Hodge numbers, so this would be HI, MI, M minus I, and have an associated geometric Hodge polygon. Let's call it A. So as in the case of the Hodge polygon you have there, and it clearly, this geometric Hodge polygon is just a fancy way of writing down the Hodge numbers. And somehow the main point of this whole business is the following theorem due to Maser, Nygaard, and Ogus, which tells you that if your crystal comes from geometry, so if it comes from HM from the mth crystalline cohomology of some nice variety, then the geometric Hodge polygon coincides with the Hodge polygon simply in terms of the F crystal. In other words, the F crystal in fact encodes the Hodge numbers, and the Newton polygon lies on or above it. And that partly answers your question. From that you can work out, if it comes from geometry, you know what the Hodge numbers will be. If it's a nice variety, I will make this precise. And there is only a finite possibility of possible Newton slopes and possible Newton polygons, in fact. But this is more a question now in convex polygons then. So, Maser, Nygaard, Ogus, it says that let X be a smooth and projective variety of an algebraically closed field of characteristic P, fix M, and let we mod out torsion and let associated to HM Chris. Then, first of all, and the first statement is that the Newton polygon always lies on or above the geometric Hodge polygon. And the really nice situation, so for all t and the allowed for all. And in case the variety is even a little bit nicer, namely if HM Chris is torsion-free, and if you've done the exercise from yesterday, you know that this, if crystalline cohomology is torsion-free, that you see that the Hodge numbers and the Betti numbers and everything matches up nicely. So if this is torsion-free, and the second condition is that the Hodge deRham spectral sequence, deRham spectral sequence, degenerates at E1. So for example, this is the second condition by the linear illusie is the case if you have a lifting over WK and P is bigger or equal to the dimension. Yeah. Then what you have is that so this makes precise for all T. So this tells you that if you have a nice variety, then the Hodge polygon, which encodes the Hodge numbers, can be read. I mean, the Hodge numbers can be read off from the F crystal, and there is this other datum, the Newton polygon, and we know at least it's on or above.
In part one of the theorem, do you actually get that the Hodge polygon lies above the geometric Hodge polygon?
Oh, I have to think about that. I mean, I'm not sure how they are related in general. I mean, because to be honest, I mean, you have to look at the pathological ones, right? And I mean, to have really, I'm not sure. I mean, it might be an interesting thing to work that out, say, for Enrique's surfaces in characteristic 2 with supersingular or something, to see what's happening. But I don't know. Okay. In case you wonder, you cannot move 2 boards at the same time. It's not that I'm not able to press 2 buttons at the same time. Yeah.
The condition you want Hn is 43 or Hn plus 1.
Oh. Sort of what I wrote down is, let me. Okay. Let me say for all M. I mean, I have to check. I mean, I think you can say a little bit more, but this is more of a survey lecture, I guess. Yeah, I guess you may be right that it should be Hm plus 1 because that would contribute via. That's the thing that comes. Let me say it this way. I mean, I'm sure you can say a little bit more, but then. So the upshot is that if X is a nice variety, then the F crystal sees the Hodge numbers and the and we have this other invariant. And I should say so upshot F sees Hodge numbers in nice situations. There is also a theorem of that tells you that if you are in a family, then suppose that you have a nice a flat family of varieties, and suppose that all the conditions are here are satisfied, then what is true is that the Hodge numbers are, in fact, in this case, then constant. Because if they have to jump, I mean, there's no space if crystalline cohomology is constantly torsion-free for them to jump. Then you can ask, so the Hodge numbers stay constant, so the Hodge polygon will stay constant in the family, but what turns out to be true is that somehow the Newton polygon under specialization can kind of, there is a relation between, if you have a degenerating families of varieties, how the Newton polygon can degenerate. Namely, what can happen is that under generalization, it can go down, and under specialization, the Newton polygon can kind of jump up. So this tells you that the most general case is the one where the Newton polygon coincides with the Hodge polygon. That's the generic case, and that's called, that's one way of saying ordinary. So I should say there are many notions of ordinarity around. So that's kind of in terms of these. So ordinary would be that Hodge, I always wrote it like, so that NWM T is Hodge, T for all T. And this condition is open. In flat equicharacteristic families. And smooth. And the other extreme is that the Hodge polygon is something, and that the Newton polygon is simply a straight line. And that's kind of, that's what people call supersingular. So you can ask what happens if the Hodge polygon is already a straight line. So, I mean, I should say you should be careful with these notations. There is many notions of being ordinary around, and of course, for abelian variety, everything is nice, everything just coincides. But if you try to generalize that, so for example, a supersingular Enriquez surface, also ordinary Enriquez surface in the sense of Bombieri-Mumford are supersingular in this sense. So be a little bit careful with these notions. I mean, they come from different times. It is a straight line. So only one slope.
You associated this theorem to August and Berthold, but doesn't it include areas by UZ, this complex theory?
This, I mean, I think this was earlier. You don't need the Rham-Witt complex here, but, and, yeah. I mean, yeah. I mean, many of these things, I mean, can be reduced to cases of varieties over finite fields, and then somehow the wave conjectures come in, and then you have to show that things behave nicely. I mean, no. Okay, so I think, already. Okay, so from what I see from the chairman, I think that's a very good place to stop here today. And I will discuss in my last lecture tomorrow, I will discuss the extreme case, namely supersingular K-free surfaces, and say a little bit about them tomorrow. Thank you.